and hopefully I can finish this today, even though just flush 15 minutes out of the toilet. Okay. Oh, sorry, maybe it's not a good chalk.
Oh. There's a good one in your office on that leg.
Yeah.
I only took one piece.
One good
Chalk.
piece.
It was just me. Yeah. Piece. I had to teach a lesson this morning.
How did it
Oh
go?
yeah, how was that? Nerve-wracking, but it went well. What?
Was it just what I said it was?
What do you have to do? The quadratic formula. What else did you talk? Did you sing the song? I did not, because it was very nerve-wracking.
What song?
The opposite, the
Okay. Yeah.
Y'all ever heard that? That's how like guys, Taco's the weasel girlfriend.
Oh, this could sound so funny on YouTube, I guess.
Well, I was gonna sing it, but then I was really nervous.
Oh, okay. Yeah, but this is the difference between a university that doesn't have resources and one that does, because here I'm scrounging through classrooms for little nubs of chalk, or a marker that works. Whereas at Stanford, at every single classroom, there's a chalkboard, there's a box up to the side that's full of fresh pieces of chalk, or there's plenty of working markers if it's a whiteboard, and yeah, because they have like money and stuff. Oh well. Okay, Gaussian Quadrature.
But do you guys have models?
Now we do, but yeah. But yeah, when I was first there, there was a big drought going on. They shut off the fountains, and they would not serve you water in restaurants unless you asked for it and stuff like that. Okay, now what we don't have for Gaussian Quadrature, and it showed you it has a high degree of accuracy, and the weights are always positive, but did not give an error formula. It's funny how sometimes it's written Gaussian quadrature and other times Gauss quadrature. I guess either term is acceptable. Okay, so what we have is I use this notation that's fairly common. Capital I and a function g in square brackets, and that's just meant to refer to the shorthand for the integral, so the exact integral of g on your interval AB. And that's going to be approximated by, let's see if I can do this on the board, your Gaussian quadrature approximation. So fancy g sub n, with n nodes, and okay, I think in the past I've numbered the nodes from 1 to n. I don't remember if that's what I did before, but in the nodes it's 0 to n minus 1, so we'll just go with that. Okay. And then we evaluate at the nodes with our roots of an orthogonal polynomial, and then we have our weights. Okay, so what would be the error? Now, the thing is, normally what we would do to get an error formula is we say, okay, this is equal to the integral, the exact integral of some polynomial interpolant of degree n minus 1. So this interpolates g at the nodes. And you might think, okay, maybe we use this to come up with an error formula, because you could use the error formula for Lagrange interpolation. But the problem with that in this case is, this would only show exactness up to degree n minus 1, when we already know we have exactness up to degree 2n minus 1. So using Lagrange interpolation doesn't account for that at all. So we're going to use a different approach. And what it will do is actually use not the Lagrange interpolating polynomial, but the Hermite interpolating polynomial. So, so I'm going to let G2n minus 1. What? All that noise? Yeah, that's my dang thermostat. And I'll tweak it to stop the noise, and then it'll do it again. So.
Yeah. At first I thought I was the only one here. Yeah, like, that's terrible. And another example of a school that has resources.
Yeah, because like you hear a noise, it's like is something getting ready to blow, or
Right.
except the only way to stop the noise was to turn it further down, which makes it colder in here.
Are you serious?
Yeah, because if I turn it up, instead of hissing, it starts blowing, and so yeah,
Oh, is that the thermostat for in here?
I guess it is. Yeah.
Oh, this whole half of the hall.
Yeah. Okay. So if I let G2n minus 1 be the Hermite, interpolating polynomial, of capital G, and of course it interpolates at these nodes, x naught up to xn minus 1. Now this seems like a strange thing to do, because an Hermite interpolating polynomial interpolates G at these nodes and G prime. But G prime does not play a role in our approximation at all. So it seems like this should be totally wrong. But Gaussian Quadrature works in funny ways. So you'll see. So what we have is we have a formula for this from before, where we have the value G at the nodes times these polynomials that kind of play the role of Lagrange polynomials. We work like with something like this in the first take-home, where this one is equal to 1 at one of the points, 0 at all the others, and its derivative is 0 at all the points. And then we have G prime times these other polynomials, the k's, that are equal to 0 at all the nodes, and its derivative is 1 at one of the points. So what we're going to do is we're going to measure the error in Gaussian quadrature by looking at the difference between the exact integral and the integral of this. And then we can use the Hermite error formula, which is similar to the Lagrange one, to understand what the error in Gaussian quadrature is. Okay. Now, so some facts I want to recall about Hermite interpolation that we're going to need. So each hi is equal to Lagrange polynomial, degree n minus 1, squared, times 1 minus 2 Lagrange prime at xi, x minus xi, and then each ki is equal to Lagrange squared times x minus xi. Okay. So what I'm going to do now is I want to take the integral of the Hermite interpolant and try to simplify it. So that's going to be just using this form down below and simplifying as much as I can. We'll have g of xi times the integral of hi plus g prime of xi ki. Okay. Now, another thing I'll need is, and you can define, I've used this kind of expression before, pi n of x is a product of linear factors of x minus each one of the knobs. Okay. And using this, I can write each Lagrange polynomial as this polynomial, pi n of x, but I'm going to divide it by x minus xi, because when I plug in xi, I want to make sure I get 1, but I'm going to get 0 if I plug it in here, so I cancel it. And then down below I have pi n prime at xi, because this is equal to xi minus x naught, xi minus x1, etc., down to xi minus x n minus 1, but skipping xi minus itself, because we don't want to divide by 0. So in other words, that is the denominator of a Lagrange polynomial that we normally see. So this is another way of expressing it. And if you've done my 685 homework, you've seen this of a form of Lagrange polynomial. And this is a form that's going to be more convenient for what we're doing. Okay.
So that's how you do that problem?
Oh, about finding the weights. Well,
Three?
yeah, yeah. Well, you arrive at that form in a different way. Here, I'm just going to,
Right.
yeah. Okay. All right. Yeah, because you could show that it's equal to this directly. Yeah. Okay. But yeah, so in that problem, you have to get this in a different form to show it the eigenvector
I
components.
just didn't know what that was or where it came from, that's all.
Ah, okay. Yeah, because if you take this and differentiate it, you got to use the product rule a zillion times. And when you plug in xi,
Everything's going to go away.
except for that one where it's differentiated, yeah. Okay. So now that I have this, I can see what I can do with these expressions here. So I need to simplify these. Okay. So first, integral of hi. So I'll fill in what that is. The formula. So we have Lagrange squared times, and I have 1 minus that whole mess. So I'm just going to break it up into two integrals. So basically, I'm taking the Lagrange squared and distributing it. 1 minus 2 prime at xi times x minus xi. Okay. Now, oh, whoops, sorry.
Yeah.
I don't have a 1 minus because I already accounted for that over here. So, okay.
Okay.
Yeah. Oh, now what I can do is I can pull a constant out. So this part I can keep the same. So 2 ln minus 1 I prime at xi is plugged in, so that's a constant. And I have Lagrange squared times x minus xi. Now what's interesting is Lagrange squared times x minus xi, we have that on the previous board. See be where? Ki. Yeah, so I needed to integrate Ki also, but now we can do that over here, so I'll kill two birds with one stone. Okay. Now, this integral of just Lagrange squared, we saw that last time. What did that turn out to be equal to? Yeah. Yeah, the integral, okay, the weights are defined to be the integral of Lagrange by itself. But we showed last time it's also equal to the integral of Lagrange squared. And that's how we can see that its weight is positive. So that is just for weight. And then we have this other stuff. Now, for Ki, I'm going to write this out as, okay. Here I have all the linear factors, x minus a node, twice, except for x minus xi. Well, actually, I'm going to just fill in our formula from below. So I have pi n of x squared over x minus xi squared pi n prime of xi squared. And then I have x minus xi. Okay. So now I will simplify that as much as I can, or like see what I can pull out. So for one thing, I can pull out this. And then what's left is, okay, one of these will cancel with that. So now I have pi n of x over x minus xi, and then I have the other pi n of x over here. Okay, now, this is probably linear factors corresponding to all the nodes. Now, how are the nodes for Gaussian quadrature determined? Where did they come from last time? Not sure what thing you were vaguely pointing at.
Well, I thought it was the summation whenever I thought those were your nodes, whenever you multiply the function times the weight.
Well, yeah, but where do we
The
get?
nodes came from Google.
Oh, well, yeah, you can find them there, but
Yeah.
mathematically, where do the nodes come from? How do we get them?
Give us a hint, because I feel like I know this.
That's for a general interval, but okay. Because when was the last time to figure out like how to make the interval exact for polynomial up to degree 2n minus 1? Is we got the error to become 0 because of or you can look at your notes. Roots of what? What is Qn? Yeah. Yeah, so they come from polynomials that are orthogonal to all polynomials of lesser degree.
Oh, yeah.
So that's what this polynomial is. So this is orthogonal. So first of all, this is degree n, and is orthogonal to all polynomials in degree n minus 1 or less. Now, what's the degree of this?
N minus 1?
Yeah, because this has all the linear factors. We're canceling one of them out. So this is degree n minus 1. Therefore, what happens here?
Degree n minus 1 times 1. Wait, you add them or multiply?
Well, they're multiplied. This is the inner product.
Oh.
And if you have the inner product of but it's because this polynomial is orthogonal, yes,
Oh, it's going to be 0?
yeah,
Because it's lesser degree and
Yes.
it only equals 1 if n is equal to n. Or, if,
or it's
yes,
going to be non-zero.
degrees,
Yes. Yeah, so this whole thing is 0. So all of that goes away. So we're left with Wi.
Wow.
Yeah. And it's only because of, this would not happen in general, but because of the orthogonality it works. And because, so that means the integral ki is 0. So that means that, if you look at what I had earlier, the integral of the Hermite interpolant, which I expressed earlier using these summations, all this. So all of that condenses to, all right, so we had a sum of g of xi times this, but that turned out to be the weight. And then the other part, the summation of g prime in all the nodes times the integrals of the k's, all that turns out to be 0. So so this is very strange that normally you think, okay, you have some quadrature rule, and the approximate integral of your f is the exact integral of your Lagrange interpolant. But when it's Gaussian quadrature, your approximate integral is the exact integral not of your Lagrange interpolant, but your Hermite interpolant. It just happens that you don't need the derivative terms because those integrals turn out to be 0 anyway. So what that means is the error, which I'll abbreviate using E of g, so that would be the exact minus the approximation, the Gaussian quadrature approximation. But now I can express this as the integral of your true integrand minus your Hermite interpolant. And this we have an error formula for from way back in chapter 6. So that would be the 2nth derivative of g at some unknown point dependent on x over 2n factorial times the product of all these linear factors squared. And because this part is definitely going to be non-negative, doesn't change sign, I can use a weighted mean value theorem for integrals, and I can pull this part out, evaluate at unknown point. So second derivative, 2n derivative at squiggly over 2n factorial integral of all these linear factors. So this is, all right, so this is my error. So here's your error formula for Gaussian quadrature. Okay. Now, what's interesting about this error compared to other error formulas is how we know this part is positive. So suppose you know something about the sign of your derivatives of your integrand. Like suppose g is like a function like 1 over x or an exponential, where you can definitively say the 2f derivative is always positive or always negative. If you know that, then not only do you have some indication of how big your error could be, you also know something about the sign. Is the error positive or negative? And if you know that, that means that you could say your Gaussian quadrature approximation is either a lower bound or an upper bound. So So that's something that can be very helpful. For instance, if you're able to get, for instance, both a lower bound and upper bound, you can say, well, now the exact integral is between these two values. So that's a little bonus you get from working with Gaussian Quadrature. Okay. Now, so any questions about how this was derived? Yes?
Based on the formula that we had previously for error, so that must be pi x minus xi to the power of 2n.
Not here?
Yes.
Well, each individual factor is squared.
I mean, I've seen this one. This is correct. But I mean, based on comparison with this one.
Okay.
So,
Okay, I'm not sure what you're asking.
I mean, the power of that g function and the factorial and that pi
Yeah.
must be the same. Right?
Well, yeah, the overall power of this, the degree of this has, yeah, the degree of what's in here must match the order of derivative and the factorial.
Okay, I mean, I got it. This is integral, right? You're right.
Okay.
I mean, for sure you're right. How much you're writing?
I always chuckle inside when a student says that. Oh, you're right.
Yeah, I mean, this means that, I mean, we knew that you're right, but again, it's just, we're confirming that you're still right.
Okay, that was fun. Yeah. Okay, and now, where was I? Oh, okay. Any other questions about this? All right. All right. So now, and I think this coming up with this error formula and everything that happened to get it is a perfect example of why orthogonal polymers are so nice. Because in a way, they're so destructive. They make so many things equal to 0. That makes things so simple. That would never happen with any other situation. So, if I'm presenting something related to orthogonal polynomials and I ask them, what is this equal to? You might as well just say 0. It's probably a really good guess. Okay. So next thing to prove, and I mentioned this result last time. Okay. So I assume that f is a continuous function on AB. So that's what that means, in the space of continuous functions. I used this notation before, but I only used it once. Gn, so fancy G. So that is the n-node Gaussian Quadrature approximation. And as before, I'll just put all notation here so it's in one place. I of f is the exact integral of f. So now what I'm going to prove is that the limits as n goes to infinity of the Gaussian Quadrature approximation is the exact integral. So like I said last time, this is something that does not hold, for instance, for n-node Newton-Cotes approximations because the weights get all screwy. But for Gaussian Quadrature, see the positive weights make it converge. Okay. Now, let's see. So I'm going to recall a theorem I mentioned some time ago, like in an earlier chapter. Weierstrass theorem. The Weierstrass theorem says that it says that for any epsilon, there exists some polynomial p of x and it has some degree, a so-called capital N, such that the infinity norm of f minus p, of the error, is less than epsilon. Actually, for some reason, book used less than or equal to, whatever. Okay, now, the thing is, if you choose epsilon really small, then you're going to need a really, really high degree polynomial to make it happen. But the point is, if you're willing to go to whatever degree it takes, you can find an approximation that's that accurate. Okay, and so I'll be working with this polynomial p, and we'll just assume it has degree capital N. Okay, so actually, I'm going to refer to this polynomial as p sub capital N. So this is a polynomial that approximates f to within epsilon. Okay. So this is what I need going forward. Okay. So in order to show that the error in my Gaussian Quadrature approximation will converge to 0, I need to show that I can make this error arbitrarily small. So I have the exact integral minus my Gaussian Quadrature approximation. Okay. I'm going to bound this error by introducing some terms. I'm going to bound this in 3 stages. So I'll have my, so I of f, that's the exact integral. But, all right, so this is where I of f comes from. But now I'm going to subtract off, inside the integral, p capital N of x. But because I've just subtracted it off, of course I have to add it back in. And then I'm going to add and subtract something more. Well, minus the Gaussian Quadrature approximation of p capital N. And then, because I subtracted this off, I have to add it back in. And then I can subtract off f. Now, I skipped a few tiny steps in between, but I mean everything we're dealing with here, integrals, approximate integrals, they're all linear. So really what I had before is gn of pn minus gn of f, but I just absorb it into one thing. So does everyone see why by adding and subtracting 4 terms that the left side is equal to the right? All right. So now I'm going to group these. So this is one part. I want to make it as small as possible. This is my second piece. And this is my third piece. I'm going to treat each of these separately. Okay, so first, for the absolute value of this integral, f minus p capital N. Okay. Dang it. Okay. I just realized why I had something in my notes the way I did. I had epsilon not in here, so so that epsilon should be epsilon naught. There'll be another epsilon later. Okay. Dang it. Okay. So this part, I could say this is less than or equal to, and this is a common manipulation to make when you're trying to show, like, kind of an upper bound on something, that the absolute value of an integral is less than or equal to the integral of the absolute value. Okay. But this is less than or equal to the integral, because I can bound this by its maximum value. But that's just going to be the infinity norm of f minus p capital N, because from chapter 8, the infinity norm is just the maximum absolute value on the domain. But this is less than or equal to epsilon naught. So I'm going to, so this is less than or equal to epsilon naught times the integral from a to b. Now, I could just say this is b minus a, but I'm not going to do that. I'm going to call this capital W. So capital W is the integral from a to b. And the reason why I'm leaving it that way is this whole proof that I'm doing, I'm not using a weight function. But if I did, everything I'm going to do still applies. But I would have capital W being the integral from a to b of the weight function. So here I have an implied weight function of 1. So if you have a weight function wx in your integral, the entire proof will be exactly the same. It's just that capital W is now the integral of that weight function. Okay, then I should probably go back and make my notes more general. Bless you. And make my notes more general, but whatever. Okay. So this part is less than or equal to epsilon naught W. Okay. Now I have these other two pieces to deal with. So questions to this point? Okay. Now, the second piece, so that would be the exact integral of p capital N minus the Gaussian quadrature approximation of little n nodes of p capital N. Now, this is actually going to be 0. In other words, this will be exact as long as capital N is less than or equal to 2 times little n minus 1, because the n-node Gaussian quadrature approximation is little n, is exact up to polynomials of degree 2 little n minus 1. So as long as this is a low enough degree, it'll be exact. So in other words, you must have little n greater or equal to big N plus 1 over 2. All right, so in other words, we can make this part of the error 0 as long as we choose the number of Gaussian quadrature nodes large enough. Okay. So we wanted to think about that. And finally, the last part of the error, we have Gaussian quadrature approximation of P capital N minus F. So that's going to be sum of this integrand evaluated at the nodes times the weights. Now, I actually want absolute values for all this. Now, by triangle inequality, this is less than or equal to the sum of absolute value of this times the absolute value of the weight. Now, this part right here, that's less than or equal to epsilon naught, because this is, well, or yeah, this is certainly less than or equal to the infinity norm of Pn minus F, and that is less than or equal to epsilon naught. Okay. So I can pull that out. So this is less than or equal to epsilon naught times the sum of the absolute values of all the weights. But the thing is, the weights are positive for Gaussian quadrature, so I can actually drop the absolute value. And when you have a sum of all the weights, that is just the integral of what?
This whole thing just cancels itself out. Oh, it's 0. It was supposed to. Never mind. Just kidding. Because we were proving that it's exact. Okay.
Yeah. Well, okay. Not everything is going to go to 0. But that, I'm so glad I got that on tape. This is capital W. Okay. So I'm writing integral of 1. Okay. So. I'm so posting at. Okay. All right. So now, if we put everything together, that means that the error overall is less than or equal to epsilon naught W plus 0 plus epsilon naught W again, as long as n is large enough. Okay. So it's less than or equal to 2 epsilon naught W. So, so now I'm going to let epsilon be equal to, or epsilon naught rather. Okay. I'll choose any epsilon greater than 0, so that's totally arbitrary. And therefore, epsilon naught is going to be epsilon over 2W. So what that means is, if little n is sufficiently large, in other words, it relates in this way to the degree of a polynomial that approximates f closely enough, the error I of f minus g n of f, absolute value, should have that up here too, is less than or equal to epsilon. So by the definition of a limit, basically like a limit, you think of a limit as a sequence, and you've had so much fun in a real analysis. That the limit as n goes to infinity of the error for a little n node Gaussian quadrature rule is 0. All right. Now, a very important part of a proof was the fact that we knew we could drop the absolute values going from here to here. So it's an extremely important point that the weights are positive. Because for a Newton-Cotes rule, even though the sum of the weights is always b minus a, the sum of the absolute value of the weights is unbounded. We saw, like, if I tried like 20 nodes or something like that, and on the interval like -1 to 1, and the weights got up to over 100. So this part cannot be bounded for Newton-Cotes. That's why this kind of result does not hold for the rest situation. But for any Gaussian quadrature rule, with orthogonal polynomials with respect to any weight function, it does work. Okay. So that's why positive weights are very important. And in a lot of real applications, people are using Gaussian quadrature nodes with a large number of nodes. Like in my own research for KSS, I don't use very many, but those that do, they know that they're getting something highly accurate that's guaranteed to be as accurate as they need it to be, as long as they choose enough nodes. Okay, so any questions about how this was finished off? Okay, so in case you thought you'd never see epsilon k proof again. All right. Okay. So I'm doing on time. Oh, okay. Well, because there's one section on composite Gauss rules, and I really don't care about that, so I'm not going to do it. It's terribly uninteresting. Okay, so that'll let me finish a few minutes early. But I have one last thing to bring up, and I won't go into much detail on it, but it comes up in research as well, so it's worth mentioning. Okay. So there are some variations on Gaussian quadrature. So first is Gauss-Radau quadrature. Okay. And so what happens in that case is because with Gaussian quadrature nodes, they fall where they fall. You have the roots of a orthogonal polynomial. You know they fall within AB, but otherwise there are no convenient formulas for them. You just use whatever works. But with these variations, you are allowed to prescribe one or two nodes. So Gauss-Radau, you prescribe A or B as a node. Okay, I should mention. So what you get is a total of n plus 1 nodes. So you do n nodes that are like Gaussian quadrature-like, and then you throw in one more. And so that makes the degree of accuracy 2n. So normally if n Gauss nodes and you have degree of accuracy 2n minus 1, you throw in one more node, you get one more degree of accuracy. Now, actually, yeah, I don't have my notes because the other nodes are not the Gauss Quadrature nodes. So all the nodes end up changing. If I have time, I can give detail on how it's done. But I want to make you aware of this. This is also something you can Google. And there is a problem about it in the textbook. I don't recall if I assigned it. I don't think I did, actually. Because it's kind of a pain. Okay, so that's one version. And one of the nice things about this is, depending on whether you choose A or B, so your error formula is, so 2n plus 1 derivative at an unknown point over 2n plus 1 factorial integral, and then you have your, for Gauss, the other nodes, the unprescribed nodes, those linear factors are squared, and then you have x minus a as a linear factor, or x minus b, depending on which one you prescribed. And the thing is, x is between a and b, so if it's x minus a, it's always going to be non-negative. If it's x minus b, it's always going to be non-positive. So, so once again, as with Gauss quadrature, you can determine the sign of the error. So for instance, here's what you can do. If you do a Gauss-Rado approximation of your integral with prescribing x equals a, then you get like a lower or upper bound. And then you prescribe x equals b and do it again. That will be the opposite, because whatever happens with this derivative of all this other stuff, x minus a or x minus b will definitely have opposite signs. So that allows you to bracket the exact value of the integral. You know it'll be between those two bounds. Okay. Now, the other variation of Gaussian quadrature. Oh, God. Where's mine?
That's okay. I was just saying.
Oh, yeah. Okay. Is Gauss-Lobato quadrature. And that's very similar. You prescribe as nodes x equals a and x equals b. And that also can be used to get either or lower or upper bound depending on the sign of your derivatives. So you get n plus 2 nodes, and the degree of accuracy will be 2n plus 1. Okay. So each prescribed node bumps up your degree of accuracy by 1. And you get a similar error formula like as to this, but you'll have 2n plus 2 throughout, and you also have x minus a times x minus b. So this part of the error is always going to be negative. Okay. Bless you. Haley, this plays a part in we're talking about the non-homogeneous boundary conditions. How can source term? Okay. No, use Lobato because him doing these nodes, we can get away with very little work.
Okay.
Yeah. Okay. Okay, so during the last few minutes, I can say something about how you would actually get these nodes, because also how you would get Gaussian quadrature nodes in general. Because if we recall the recurrence relation for orthogonal polynomials. So beta, j, is equal to x minus alpha j, q j minus 1, minus beta j minus 1, q j minus 2. Okay. So this is a three-term recurrence relation that gives you all of your orthogonal polynomials where you have these formulas for the alphas. And this was also pj of x is equal to all this, so it's q. So that's your formula for alpha j, and then beta j squared is equal to the inner product of pj with itself. Now, so one nice thing is if I form this matrix, a tridiagonal matrix from the alphas and betas, and it's symmetric. And this, okay, so this holds for j greater or equal to 1. Alpha 1 alpha n, and then betas on the subdiagonal and superdiagonal. Okay. So what happens here is the eigenvalues, this will be familiar to almost all of you. So the Gaussian Quadrature nodes are the eigenvalues. And this is probably the best way, from a numerical standpoint, to compute for roots of Qn. Because you don't want to compute the roots of Qn using other means like Newton's method or other root finding methods, because round-off error accumulates as you go from one root to the next. But the symmetric eigenvalue problem, and this is something that will be covered more in depth in 610, is it's a very numerically stable problem. It's very well conditioned and all that. So, especially in this case where we know the eigenvalues are distinct. Plus, it's also pretty cheap to solve to get the eigenvalues of this because it's tridiagonal. So this is a preferred way to do it if you have to go to the trouble of generating your orthogonal polynomials using a free-term recurrence relation anyway. This is a way to do it. The process of generating this is similar to like what you know is the Lanchell's algorithm. That it's reminiscent of that. And the way to do Gauss-Rabel or Gauss-Lobato is basically it involves taking this matrix and extending it, still a tridiagonal matrix, like you add a row and column basically, in such a way that you're forcing an eigenvalue of this matrix to be A or B, or in this case for Gauss-Lobato, A and B. This is so the papers that my advisor, Gene Golub, all his writings on matrices, moments, and quadrature, including his original matrices, moments, and quadrature paper, discusses all this for certain cases anyway. So it's very well documented out in the literature how you do this. I just don't have the details in front of me, so I don't want to make an ass of myself and try to cover it. It's not easy, also. But it's a pretty slick piece of numerical linear algebra, so that's one thing I thought was pretty cool about it. So, all right, that is Gaussian Quadrature. And now you're all set to do the second take home. I know. Oh, and I'm exactly out of time, so that worked out beautifully.